Welcome. This is going to be a tutorial on using TensorFlow and Keras to code up some neural networks in a Python notebook. And I'm going to also provide the notebook. So if you go into my GitHub, which is W. Basner, select the repository neural network from scratch in Python. And then in here, you go to M26 tutorial neural nets with Keras. There's a Python notebook that provides a neural network from scratch, meaning just using NumPy in there. And then we want to open this notebook in Colab. And I have a button here that we can do that. At this point, you might need to sign in to Google to access the Google Colab. Okay, so, and you could see the sections that we're going to be going through on the left-hand side there. So let's get started. First thing we want to do is going to import some basic functions and libraries. We're going to import sklearn, which is scikit-learn, which is a package you should be familiar with for machine learning, or by which I mean we're going to walk through the pieces. You don't have to be super familiar with to walk through this with me, but it's a good one to know. So then we're going to import TensorFlow, and this is a nice feature of working in Google Colab that you have the TensorFlow set up for you, library, so you don't have to do a pip or conda install, which can be tricky with TensorFlow. And then we're going to import NumPy and OS. We're going to set a random number seed, which means you will get the same results that I do when you run this. And then this sets up our nice figures in matplotlib. And all of this is to do save our figures as we do plots. And here we're going to suppress our warning. So to run a block, we hit the run button. It often says, hey, are you sure you trust this? And of course, I do. So I run it. And this tells me it took 0 seconds to run this block. And then there's a little kind of warning on here, and this tells me the version of TensorFlow that I have is 2.11. So now we're going to do some work. First, we're going to build perceptron. So let's go through this. First, we're going to import NumPy. We're going to import the datasets and import the load iris function, which will load the iris dataset that was collected by Ronald Fisher, 1930s or so. And we're going to import this linear model, which is a perceptron. A perceptron is just a neural network with one neuron. And so here's the iris data. We're going to call it just iris. And it has 150 irises in it. And there's 4 features or 4 measurements on the iris for each observation. So petal length, petal width, sepal width, and here we're going to pull out the petal length and petal width. Those are the 2 we're going to use. And we are taking the y variable in here. We're going to turn this into an int. So this will check where that's 0, and it'll set equal to a true where you have a 0, but then we want to turn it into an int. So we're going to have 1s where that was a 0. And then here's where we make our perceptron. So it's per_CLF, so it's perceptron, and CLF is a standard notation for building a classifier in Python. So max iter, so we have some parameters that are common here. That's the number of iterations in training. Tolerance is actually, I don't know specifically what it is here, but usually that's a parameter on, I don't think we have to compute any covariance matrices here. Sometimes there's a covariance matrix. Sometimes it's we're going to run our iterations till something ends. I guess we can go ahead and take a look at that. So sklearn perceptron. So if you're ever curious about parameters or what you can set, yeah, okay, so max iter says we're going to run up to 1,000 iterations, and then the tolerance here is a stopping criteria. So the specific criteria here is the tolerance is going to tell us this equation. So we're going to stop iterating when the decrease in loss is not greater than this tolerance. Yeah. So we're going to, as we iterate, our loss should be going down, but when it doesn't increase by at least that much, we stop running. Now we tell it to fit to our data, and then we're going to do a prediction on an observation where the measurements are a petal length of 2 and a petal width of 0.5. Okay, so we already ran this. We hit run again just to see it run. It took 0 seconds to run, so that's nice and fast. And we get a little warning, NP int is deprecated. So you'll often see this in TensorFlow until things are updated. So that should be replaced by just int, but it's just a warning. It runs. We could suppress that warning if we wanted to. And then we want to take a look at Y prediction, and that gives us a prediction of a 1. So we're in class 1. Now, what we're going to do here is A is going to be negative. A and B are going to give us the okay, so Y pred is our prediction on that 2, 0.5 observation that we made up and put in, and it says it predicts it as class 1. Okay, let's take a look at the output, and really the things we're going to be doing here are just generate this plot. So let's take a look at how we're going to generate that plot. Here, this is our perceptron classifier and the COEF, if we want to see what that is. We come into the documentation for the classifier and we look at the attributes. And this is the weights that are associated to the features, which turn out to give us the separation line that it's found. And so if we can pull that out from the A and call A the slope, and then we're going to use that to plot the line of separation, and B is going to be our intercept for that separation line. Then we're going to set up some axes. We're going to build a mesh grid, and what this does is in Python, this allows you to build a grid of X and Y values, typically so you can run your classifier on a broad set of values and visualize. Then we're going to make this X new, which is this grid of values, and we're going to predict on it. And then ZZ is going to be the results of predicting on that grid, or predicting for all values in that grid. And that's really what we're going to use to give us these two shaded regions. Now we're going to set up our figure. So it's a 10 by 4. So 10 is the width, 4 is the height. And then these two plot functions give us a plot of first the X values at everywhere where Y is 0, or for class 0, and this is everywhere where we're in class 1. And so the zeros are the non-iris setosa. So this class that we've picked out is the setosa species. Then we're going to plot the line. Then we set the color map here, and we build this custom color map, and that's where we use to color the blue and the yellow for our background. And that's where the blue S and the yellow O come in. The yellow O is a yellow circle, and then the blue S is a blue square. to designate our two classes, our data points, so the blue squares and the other circles we can see here. And then we set up just our labels and our legend, and then we're going to save this as a figure and then show it, right? And just to see if we switched this figure from, let's do one little thing to switch on here, make it size 10, 6, and recreate that figure. We'll just get a figure that's a little taller in this case, right? So maybe that might be something you'd like. Okay, so that's a single neuron. The reason we don't use just a single neuron is because we want to build a nonlinear separation surface in higher dimensions instead of just a line. So let's take a look at the activation functions. What an essential part of a neural network is we take in a bunch of feature values, we multiply them by their weights. Sometimes we add a bias, and then we set that through an activation function. We need an activation function. If we don't have an activation function that's nonlinear, then our whole neural network just becomes a linear classifier, and we get a line. But we need a nonlinear activation function. So here are some standard ones. Here's a formula for the sigmoid, and then there's a formula for the rectilinear unit. And then the reason we pick these type of formulas or something similar that has a simple derivative is that, well, they have simple derivatives. So here's the derivative for one of these. And this EPS is so we don't wind up either with a division by 0 or something values that are exceptionally small, right? And so this is a block of code that's going to create some plots. First one is going to be the step function that just takes the sign, whether something is positive or negative. Then we're going to have the sigmoid function, the hyperbolic tangent, and the ReLU function. So these are the most common activation function types. And really that sigmoid and the hyperbolic tangent aren't used very much anymore. And we'll see in the plots why the ReLU is the most popular. And then there's modifications of the ReLU that are also popular. This function here, if you look at the derivative, let's take another look at this. So we have f, if you're familiar with the formula for the derivative, this takes f at z plus a little bit minus f at z plus a little bit divided by 2 times that little bit. So this is the formula for the derivative from calculus, and this is our h, our kind of step size. Okay. So this is taking the derivative numerically, or it's the slope from one point to the next point. And then this gives us some nice plots. And here's a very good plots. So the activation functions on the left-hand side, derivatives on the right. So the step function is the this orange line. And you can see it's -1, and then it jumps up to 1. It's an early model that we don't use in building neural networks anymore, but it was used in early models for modeling brain activity in neurons, where it's not firing. And then once you cross a threshold, it starts firing. But it doesn't, because there's no slopes on either side, you can't use it to train, which is one of the things we're going to need, right? So if you look over here on the right-hand side, the derivative of that is just 0 everywhere, undefined at the origin. The sigmoid and hyperbolic tangent were chosen historically to model the step function, but have some slopes that would be useful for training. And so we could see the slopes here, that they're increasing and increasing they're positive with increasing slope. And then the slope starts decreasing as you go to the further right. And then there's the ReLU, which is this purple dash dot. And that has a slope of 0 on the left-hand side and a slope of 1 on the right-hand side. And so that's a really good one for training because it's such a simple derivative. And we can see for the derivatives, if we go out here like above 4, the gradient or the slope for the sigmoid and hyperbolic tangent becomes 0 out at the fringes. So once you get a neuron whose values are out there, the slope is so small it's hard to train that neuron and adjust its weights. Okay, and then there's the Heaviside function and the MLP XOR, which is something we're going to see. And we'll take a look at those, and it'll be easier to see what they are when we get to the plot. So again, we're going to take a look at some plots. And so here's our activation function being the Heaviside function, and this is the activation function being the sigmoid, and this is our XOR problem, where we want to have one class that's upper right and lower left, and another class that's the triangles. And this is a MLP, which is what we pulled here, and it's going to be this activation function. So it's going to be dependent on what you put into it as the activation function, and it's just going to take that in, and then it's going to apply that in this sort of going upward to the right direction. So this is a standard problem that, hey, we'd like to distinguish the black from the yellow triangles, the green squares from the yellow triangles, and you can't do this with a single line. You need something that that will switch from square class to triangle class to square class as you go up and to the right. So a linear classifier won't separate those. This classifier does an okay job, but it's not great, as we'll see. Okay, so now we're going to start building some things with TensorFlow. So we import TensorFlow as TF Keras, which we've done above in the first block, but just to check it. So TensorFlow version 2.11 and Keras 2.11. So what we're going to do is we're going to read in this data set called fashion minced, and then we're going to pick out the test data over here, which would be X test and Y test, and then here's the training data, which is X train and Y train. So it takes a little, might have taken time. It's only 0 seconds, so that's good. So that went quickly. So we should always start out by taking a look at the size of our data set. So we have 60,000 observations. Each observation is shape 28 by 28. And each observation is a unsigned integer with 8 bits. So that means a positive number between 0 and 255. Standard for digital images, because gives you a good visual representation on a computer screen, but still at 8 bits, it takes not a lot of memory. And so these are 28 pixel by 28 pixel observations. Let me make sure I've run both of these. I believe I did. And now what we've done in this block is we're going to take our validation and we're going to split it into a validation and training set. You can see the split here. We're also taking our data and dividing it by 255, because when we put our data into a neural network, we typically want it on a 0 to 1 scale. It's really more important to think about the real reason is so that when we initialize our weights, that they're on about the same scale as our feature value. So if we could use 0 to 255 and then initialize our weights in the 0 to 255 range, but we want to take derivatives, so we want floating point numbers, and it's easier as a standard to scale our data to a standard scale, and so it's going to be on a 0 to 1 scale, so that the real goal there is so our weights and our feature values are on the same scale, right, around 0 to 1. Okay, so we're going to pull out one of the observations. So this is from our training set. And if we wanted to, right, so we could take a look at some of the different images here. So these are different articles of clothing. And the CMAP equals binary. That'll give us a reasonably nice color map to view these. So here's the IDs or the class labels. So these are our Y values. So they're going to be values from 0 to 9. Now, these are really fashion. It's called the fashion minced data. So they're articles of clothing or fashion. And these are the classes: dress and coat and bag and ankle boot and so on. So we could check the class name for the 20th observation from the training data, and it's a sneaker, right? Just to go back up here. That's the observation that we plotted up there, that sneaker. Okay, so our validation set is going to have 5,000 images, and our test set is going to have 10,000 images. So we can just check those shapes there. Okay, now here's a little loop that's just going to iterate through some of our data and give us a plot so we can take a look at it. Class names is not defined, so it looks like I probably forgot to run that block. Got talking. Okay. Here we go. So there's our good sample of our data. Now, here we want to run, here's where we start getting into the Keras and TensorFlow code. Everything up has been on a kind of more standard Python, a little bit of machine learning. So what we're going to do is we're going to use Keras models sequentially. Really, whenever you come across a block of code with a new programming environment, you probably want to type it in and look for the documentation and take a look at the documentation. So let's go ahead and do that. So here's some information on it. So we go into the Keras and it explains how to use this. And we're going to go take a look at the model itself and use it. So we don't really need to take a look at it, but that would be useful. And you could take a look at the code that they have here in Colab. I would be interested in seeing more of the documentation for this, meaning what are the kind of inputs and outputs and such. But okay, so you could browse this. But what this does is this gives us a model. So we've created a model. It's going to be a neural network model. It has no layers in it. So it doesn't do anything to start with, but this sequential means we're just going to add layers, one layer after another, and it's going to, assuming they have the right sizes, it's going to connect them appropriately, however we declare, and build us a neural network that we can use to train. So the first layer we're going to add is going to be a keras.layers.flatten. So it's a flattening layer. So it takes our input of 28 by 28 and it flattens it, and it's going to make it a single vector of length 28 times 28. So what's that? Is that 784? Yeah, 784. Okay, so then we take that layer, that vector of length 784, and we're going to, the output of that's going to go into this dense layer. So it's going to have 300 neurons in a ReLU activation. So vector of length 784 goes into another layer. It's a fully connected layer. So every output from that 784 is going to go to every one of those 300 neurons. And then there's going to be a ReLU activation applied to that. And then we're going to have another layer after that, which is going to have 100 neurons, another ReLU. Then it's going to have go to a dense layer that has 10 neurons, and the activation here is going to be softmax. Now, softmax is a standard for doing classification. Out of these 10 correspond to our 10 labels. Each of these is going to correspond to a different label. The softmax normalizes the output from this layer to make them So they sum to 1 and that they're all positive. And it's the max here, it refers to, in this layer, whichever one is outputting the max value before we apply the activation here, it's going to retain that maximum. So let's go ahead and build our model. That's going to run very quickly because, sorry to jump around. Actually, I think I'll just close this on this side and then I can zoom a little better. Okay. Then we're going to clear any previous things in Keras. We're going to set our random number seeds so that when you run this, you get the same thing that I get. Now we're going to rebuild this again, but notice this time we're using Keras in each of these. So, and Keras is really a nice, you can think about it as a nice front end, or it makes nice functions that you can use to build neural networks in TensorFlow. So here we can take a look at our layers from our model that we built. And so this tells us the layers, and we can get a summary, which tells us the layers, but also tells us a little more information, right? This flattened layer has output 784 values. This dense layer has 300 neurons, so it's going to output 300 values. Each of these 784 is connected to each of these 300 neurons, giving us 235,000 parameters. Here we're going to have 30,000 parameters going from the 300 to 100, 30,100. So it's 30,000 and then 100 biases. So 300 times 100 gives us 30,000. And then here's our parameters going into our final model. So it tells us the total number of parameters and the total number of trainable parameters, right? Trainable and total parameters might be different. There might be parameters that are in here that are read in as part of one of the layers that don't get trained. Okay, so here's a nice utility in Keras. You give it your model and it will give you a nice figure of the neural network. So this says we're going to take in a 28 by 28 array and we're going to flatten it. And the input is this 28 by 28. The output is going to be a 784 vector. This one, the input 784. The output of this layer is 300, and then so on. We can also look into the model and examine some of the values for these layers. And so the hidden layer number 1, that's our first hidden layer. Its name is dense. So that's meaning that's the type of layer that it is. And we can check to see if it's a hidden layer. And then we can take a look at its weights and biases. So we can do hidden layer number 1, get the weights, and here are the weights. So here's the shape of the weights. So this is going from 784 to 300 on these weights. And then here are the biases, and we see an important thing here. Remember I mentioned the weights should be on about the same scale as our data that's coming in. Our weights by default in the TensorFlow models get initialized with a normal distribution, and it's a small standard deviation centered at 0. So these, as you can see, they're all close to 0, a little positive, a little negative. And so that's a big reason we want to take our data and scale our data. If we didn't scale our data and we wanted to get under the hood and initialize the weights a little differently, that would be okay, but it's much easier to normalize our data. So here's the shape of those weights. So 784 by 300, there's 300 neurons in the first layer. Each is connected to 784 outputs. And here are the biases. We typically initialize our biases to 0. That way, if the biases are initialized to 0, we're not pushing any of the neurons to be either activated or unactivated like on average, the variables coming into them should be close to 0, and a bias of 0 allows the network as it's learning to either activate or not activate the different neurons. Activate meaning the output is going to be positive, not activated meaning the output's 0. Those are the shape of the biases. Now we're going to compile the model. So the model has layers and weights, but it doesn't know how to do any training. So we compile, we're setting up the training. So this loss equals sparse categorical cross entropy. That's setting up the type of loss. Sparse categorical cross entropy is a standard loss function for doing classification. Our optimizer is SGD, which is stochastic gradient descent. And the metric we're going to be outputting as we do our optimization is going to be accuracy. So stochastic gradient descent, just to give us a good, quick picture of what that is doing. So here's a picture that's looking at our loss function, which is the sparse categorical cross entropy. And we pick an initial value, and we want to, when we're training, we're modifying those weights by a little bit to decrease the loss function. And so this plot represents a loss function. And then we start somewhere, and then we want to modify things a little bit, and we want to go downhill. So this is a picture of what happens when we do training. And one of the things we want to avoid is we want to avoid starting somewhere where we wind up getting caught in a local minima, like this example. That's not the global minima, not even a good, decent minima. So there's a lot of things that go into that optimization to avoid doing that. One of the things that goes into there is the neural networks you're dealing with a high dimensional space, so you have more potential to avoid those local minima. But that goes down the long discussion about what are the stochastic gradient descent optimizers and what does that do, and versus Atom is the other optimizer that's common. Okay, so sparse categorical cross entropy is a method where we compare the output from our neural network to the output that we want it to be. And what we want is zeros for all the classes that are the wrong class for an observation, and a 1 in the class in the vector output that corresponds to that correct class. And so this will adjust all of our weights to get our output a little closer to that based on this criteria. Okay, so let's compile our model, which is just setting those values. We actually haven't done any work, and that's equivalent to, so this is a quick way to set that up. And so we could say loss equals and then just give it the name for a loss, and we could say loss equals and then give it the function for that loss in Keras. So let's just take a look at that. It's always good to take a look at the documentation for the content that you're using. And so this sparse categorical cross entropy, there's a couple of parameters that you could feed into that to modify them. And here's where that name is if we wanted to just call it by a name. And if we want to see what other loss functions there are, right, it's really good to get familiar with the TensorFlow documentation. We could take a look at the loss functions. And so you can use this to create your own loss function or pick different loss functions. Okay, so kind of want to be at a high level and not get into the too much into the weeds. So this is the accuracy, and this is saying what optimizer we want. We're going to take the SGD, which is stochastic gradient descent, and then here's where we fit the model. So this is actually looking at the training data and then evaluating the weights and changing the weights iteratively. And so we're going to do 30 epochs. Each epoch is a full run through all of our training data. And at the end of that, we're going to use this validation data. And so this is a standard thing in Keras. We also include validation data. We're doing our fit or our training. And what it'll do is it'll train on the training data, and then it'll output the validation results of the validation data to keep us updated on how well it's training. So let's go ahead and run that. So we should see our loss going down as we iterate through trainings. So that it's gone through all of our data. And we have 1,719 observations in our training data. And so our loss starts at 0.7. Our accuracy in at the end of the first round is 75%, which is not bad for 10 classes, right? If you choose randomly from 10 classes, you would have typically a 1 out of 10 chance. So your accuracy would be 0.1. And we can see that our accuracy is increasing nicely. Okay, so we finished recording. We finished training. And let's look at our results. So early on in the training, so let's go to epoch 1. Right when we start, our loss is 0.7 and our accuracy is 0.75. That's on our training data. On our validation data, our loss is 0.5 and our accuracy is 0.8198. Interesting that our validation accuracy is higher than our training data. And we could see as we go along, our training data accuracy should be improving as we go along. Our validation accuracy, you'll notice it jumps around more, it's noisier. So it goes up to 0.85, and then it's 0.79, 0.86, and so on. And we look as we train for a while, we get down here at 30. So it's a 0.89, and that's been pretty consistent for a few iterations. And so that's after 30 rounds of training. And you'll notice here's our validation accuracy, our training data accuracy is 0.9, and then a little bit, and that's a little higher than our validation, which is pretty standard, right? We're slightly overtraining, meaning our validation is slightly worse than our training data, but that's okay. That's not a lot of overtraining. Okay, so we can look at our history parameters. That tells us what we've done for training. Verbose setting to 1 means we're going to output the indicators above. 30 epochs, each epoch has 1719 steps in it as we run through all the data. So this is in the history. So this is history epoch, history params. If we go up here, when we trained, notice we said history equals this. So we've saved all of our information from training in this history variable. And we can look at the keys that are in our history. And so there's a dictionary. So the history contains a dictionary, or is a dictionary of the results in the history, the metrics that we told it to save. So there's loss and accuracy, and validation loss and validation accuracy. So we can look using pandas, we can plot this data frame. So it says, make me a data frame out of the history, and then plot it in a figure that's 8 wide, 5 high. Grid equals true says put the grid on. We're going to set our limits for the plot and then give it a title and show it. And so here's our history from training. And you'll notice, let's look at the curves on the top, which are the accuracy. So the orange is accuracy on the training data, and we see that was nice and smooth, and it's increasing steadily. And then the red is the validation accuracy, which we said is going to be a little noisier. And out towards the end of our training, there's generally a little separation here where we continue to train, and we often overtrain a little bit. So we want to pick our best model, or maybe if we want to stop early, we might want to stop somewhere where the validation accuracy hits its max if it tails downward towards the end. And then on the loss, we see both of these are going down. the training data loss is going down steadily. The validation loss is going down a little noisier. Okay, so now we want to evaluate that model on the test data. For you remember, we have our training data, validation data, and then test data. As we're training, we're checking it against the validation data, but the test data we've never seen or run the model on yet, kind of like what we might call a holdout data set. And we see the accuracy on here is 0.88. So that's good on a classification out of 1 out of 10. And we take the third observation and we call that X new, and we're going to compute the probabilities from our model. And then the Y probability is shown right here. And I don't think I've been running these. So let me, okay, the ones with the little green check mark I ran. So I'm going to make sure I run them in case they get called, the variables get called later. And let's take a look at this. This X new is X test at observation 3. So what I want to do is put some code in here and take a look at the Y value for that. And the Y value for observation 3 is a 1. And so I would have expected it to be, oh, sorry, let me clarify this. So this :3 is taking the first 3 observations from our data, not just the third observation. So each row here corresponds to a different observation. So the first row is the first observation, and so its class is 9, which is the very last class, and the probability is a 0.96. So that's good. Second observation gets a 1 here in the 0, 1, 2, like the index for there is 2, and so that's a 2, so that's correct. And then this third observation, the predicted value has a 1 in the first index equals 1, which is the second slot, but it's index 1, and so that corresponds to our Y value. So that's good. So that means we're correct on those 3, and they look nice. And not only they look nice, but we can also be confident in those, meaning they're high probabilities and they're correct. So then we can predict on the test data, and then we can get the predictions on all the text data, but we're just going to pull out the argmax. So we're just going to say, hey, tell me what the best call is for those. And then we run on all 313 observations. So this is class 9, class 2, class 1. So our predictions here are saying, hey, give me the highest value in each of those. So we're not outputting the vector of probabilities. We're outputting an index for those. Now let's take all those predictions, which are the indices for the class, and pass those indices into the class names vector or list, and we'll get the outputs from that. So this class 9 is an ankle boot, and then class 2 is a pullover, and then so on. And then we can check. This is going through and pulling out one of the test values, looking at the Y value, so it's class 2. And so here's a plot of 3 of the images: ankle boot, pullover, trouser. So these are the iterating through X new, and we are showing the image, and then the title gives us the class name for the Y test for that image. Now, let's see. Let's modify this a little bit. And what I want to do is I want to put in the class name for that test image, and then let's do the predicted class name. And so ypred was our vector of predicted values. So we're going to output the class name, and we'll put pred equals that. So let's go ahead and, right. So this was an ankle boot predicted as ankle boot. This was pullover predicted as pullover, and this is trousers predicted as trousers. And I know that didn't show up great. There we go. That's probably a little better way to put it. And so this iterates through every observation X new. So let's go through and let's make X new length 25, because what I often care about something like this is taking a look at a couple that I got wrong and seeing where our okay, so this is going to make us an image that's probably too large for us to look at. Maybe we can scroll over. Not way too small. Okay, so let's do, instead of doing 3, instead of doing 25, let's just do 5 of them. Shirt, trouser, 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 shirt, shirt. Maybe we can do 10. Our accuracy was about 90%. So that suggests that if we do 10, we have a chance of